All right, so we're going to consider the structure of the deformation gradient, the second order tensor. In fact, as we will see today, so that can be interestingly decomposed into different modes of let's say motion or deformation that developing at a point. So we'll call it a polar decomposition. All right, so let's start from considering this stretch in the direction m. Again, m is some arbitrary direction, and so that is defined by unit vector m. So now then, if we consider a stretch in this direction and calculate the square of the stretch, then we simply can write this multiplication of stretch lambda multiplied by lambda in this way. So the only thing that we are not doing here, we are not taking root square as we have done before, and so we're calculating lambda square here, right? So before that, to calculate the stretch ratio, we just took a root square of fm dot product. Now, the one thing that we want to do here, and we want to compose this multiplication here in a little bit different way. So we'll just change it a little bit. And what we want to do, we want to bring these two f's together, this deformation gradients tensors here. So the way to do that, and we have done already something similar, is so we want to change the order of multiplication here, f and m. But if we just put m here, so we change the order. For example, if we write fm, right? So if we want to write f multiplied by m, and I'll put indexes here, so it will be much more transparent for us, which is when we multiply f and m, so that is the order of indexes that dummy that appears here. Now, if you want to do this in this way, if you want to write m multiplied with f here, so what we want to say is that still j, right? So nothing has changed, and if this is ij, so basically what we did in this sense is that we needed to but when we write it like this, so what we do, especially if we in fact even emphasize that as with dot product, when we multiply m and f in the way that we restructured here, then that would mean that this index will multiply the first one here, and to do so, then we'll need to change it, right? So that will be like this. So this is, so we change the orders. It's now f is ji, but this is not equal to this multiplication, of course, because instead of ij on the left hand side, we have ji on the right hand side. Therefore we must have a transpose here, and so in tensor notation, and I will change the color for that. So this will be written in the following way, in a way fm. So right, so this multiplication. Now we change the order, and we need to say that there is a dot product, because we typically don't multiply, don't act as by vectors on tensors, right? So that will be something like that, and that f will already multiply something else. It will continues here with these guys, right? So, but we need to actually it's important to put a transpose here to maintain to maintain the multiplication of the correct indexes of the if you think components of J and Fj. So that's basically, this is an index notation, and this is more formal tensor notation, as we will be using it right here. Okay, so with that we can continue and write it like that. So, and again, so what we did, we basically just changed the first part of this multiplication, fm, and so which became m dot f transpose, and the other part fm didn't change, and now we have here in the center this is f transpose f. Now what we're going to do in the final step here, we just introduced a new measure. So we just said, okay, let's call this f transpose f, let's call it C, and we'll give a name to that that actually will be called right Cauchy-Green tensor. So this is a right Cauchy-Green tensor. This is now we need to look into the structure of C, and so this is a multiplication of two second order tensors, so the result is also second order tensor. So that's again our definition for that, right? So when we take one second order tensor, multiply it with another, we obtain second order tensor, and actually we mean that there is a dot product between them when we write this multiplication this way. So this is so C will be important to remember for us. We'll use it a lot. It's a measure of deformation, another measure of deformation that contains this quadratic term in the deformation gradient, and also related to quadratic term in stretch, right? So this is stretch ratio in certain direction, so C is somehow related to this change, in direction, arbitrary direction M. And so what we can now write is the following. So let us assume that direction M is nothing but the direction M, for example, again, so M is at this point is a general any direction, arbitrary chosen unit vector that we want to measure the stretch in that direction. So now let's assume that that M is actually a principal direction, or in a similar way what was considered, for example, principal stresses, right? So both principal direction. So we are heading towards the structure that M will represent the eigenvector, right? So so let's say that this is a principal direction. So we can do that, and then let's just use our equation 222, right? And rewrite it in this way when we just said, okay, so M is a principal direction. So it's a principal direction, and so then we can basically use the eigenvalue definition, right? So when we can write that Cm it can be basically what it will be. That will be this part Cm. So if the M is an eigenvector that of C, of the second order tensor C, so that means that C acts on that M and produces the same vector M scaled by by some factor, and this factor is the eigenvalue, right? So if we just rewrite it, then we can put it in this way, right? So that Mi is first preserved, and so if Mi is the principal direction or eigenvector of C, so then we can write in this way when this fancy psi is nothing but the eigenvalue of C. And now, important to note here that this I here doesn't mean the summation is very common for us, right? So this rather because this is not a real index, but rather a tag or a label or name of that vector M, because we have three eigenvectors, and each of them have its own components, but we need to mark these vectors M here, so that's hence we have I. So, but there is no summation on I. And so, and since again, if we look into that, so xi is a scalar, so we can pull it out, and then we have two vectors m dot product, but because they're unit vectors, so the dot product of two unit vectors, right? So that the same one, we project one on another, so we obtain we obtain a factor 1, so and then the result will be xi. So what does that mean? That means that basically this, if we consider this second order tensor, so its eigenvectors, right? So it's mi. So what's important is that the eigenvalue of the vector c will be actually the quadratic stretch, right? The stretch square in this principal direction. So that's an important property for our new introduced right Cauchy-Green tensor. So once we calculate our right Cauchy-Green tensor, so then what we can do, we can solve the eigenvalue problems, and immediately we'll obtain the in the result of that will be again a new principal coordinate system in which the eigenvalues will define the principal stretches in that direction, in that new direction. This is very convenient for us because what that means is that we can write C in a very compact form in terms of these principal stretches that we just defined, that we can calculate based on the eigenvalue problem. Right. So the right Cauchy-Green tensor can be expressed in this way, so in 225, and what you should note here is that instead of E1, the tensor products here for the bases, we have the new ones that are defined by the eigenvalues or eigenvectors of the right Cauchy-Green tensor. So, and then of course, because they're mutually orthogonal, so they form a new coordinate system in which, okay, so C actually looks can be presented in a very simple form, so they're only diagonal terms that are quadratic terms in stretch. Okay, so this is it's important. And again, C, as you've seen, is very simply defined through the deformation gradients that we define. So it's just F transpose F multiplication that produces this symmetric tensor, right Cauchy-Green tensor. Now, for the further consideration, let us define. So okay, so we have quadratic terms. So what we want to define at this point, we want to look into our deformation gradient back and see whether we can see similar components of these principal stretches that we can also identify in deformation gradient, right? So we found this is possible for the our symmetric right Cauchy-Green tensor, and so now we will be trying to also to identify the structure in the deformation gradient. So and so for that, let's just define what is called stretch tensor, or more precisely, right stretch tensor. Right. So basically saying, okay, so C is the quadratic term, and the stretch tensor is the root square of that. So so this is our definition for right stretch tensor. So we can take C. Oh, sorry. So that's let's first focus on 226. Right. So we are looking into C. So we're defining U now through the right Cauchy-Green tensor C. So that's root square of C. right? And basically our purpose was to write the tensor that would exactly correspond to the stretch, not in the quadratic terms, right? So seeing is a structure, so what we did, we basically just removed this square signs everywhere, so the powers are gone. And the stretch tensor is basically, yes, what you expect it to be, the stretch ratios in these directions, right? So lambda 1 correspond to m1, lambda 2 to m2, lambda 3 to m3. So these are principal stretches in this principal direction. And so we here, and with that definition of U, that represents the information about how much the line element was strange at a point, right? So this information is contained in U, so we can say that any deformation gradient can be represented as a multiplication of that stretch tensor, right, and something else that is we are going to call it as rotation tensor. So meaning that, and that can be defined based on 227, that okay, so if f contains that U, and that can be defined in this way, so we can then say, okay, so we can calculate R based on this formula. Just okay, so we just take f and basically remove that part of the stretch from that, so multiply it with inverse U and see what will remain here in R. But again, going back in 227, what we assumed here, and of course that will need to look into R more closely. So, but what we assume here is that if so the deformation gradient is composed in can be split into two parts. The first part corresponds to actual stretching, and the second part can be just some rotation or rigid body motion that doesn't involve the actual deformation as we understand it, right? So that the point is not deformed, but rather, for example, just rotated or rigidly moved, which is which doesn't cause the creation of stresses, or at least not supposed to create them in a relatively simple material. But now, so we're going to look into that a little bit more, first we'll analyze this rotation tensor, because it has an important for us properties that we can use after that. And so we'll be using 227 and 228 to analyze what are the properties of this rotation tensor R. All right, again, so the rotation tensor, so the properties of rotation tensor are important for us for many main things. So again, R is an important, let's say, part of F, that we split F into R and U. So we assume, so we think that U, this part of F, U, the stretch tensor, corresponds to the actual deformation and stretching in certain direction. Then R would be some sort of including rotation. So what would that mean? That so R need to satisfy certain condition, and we're going to check that. That again, going back to F. So what we said, F is the tensor, second order tensor that we take and act on vectors and then transform vectors. So and as we multiply a vector by F, and so then when we take R and U, that means that U will come to that vector, and that when we multiply with F, effectively multiply that vector with R and U in the order that we are going to multiply that, and so U will stretch that tensor, and R will rotate it, but will not change the length of that vector. And so So for that to be true, we need to R need to be of certain structure, of certain has some certain properties. Now, and this property is so-called of the tensors that are so-called orthogonal, so to be an orthogonal, so there's the multiplication of the transposed vector with R need to produce the identity tensor. So this is not usually the case. It's for any tensor, right? So in general, that will not be the case. To produce identity through multiplication, you would need the inverse of that, of R, right? So that's so if there is instead of transpose, there would be an inverse -1, right? So then of course automatically they will produce identity. But this when you multiply transpose of the same second order tensor with itself, only for orthogonal tensor that will be the case. Now, when we are using our previous formula, 228, right? And so we basically substitute of an R, what we derived for R based on our definition. So we decomposed F into U and R. So R is nothing but F multiplied by U inverse -1, and this whole FU -1, this is R, and so now we need to transpose that, and we have also the original R, which is FU -1. Now, when we do the transposition of FU -1, so we put the transpose everywhere, but we also change the order. So the result will be U minus transpose multiplied by F transpose. That's what will be represented here. And so the results of this transposition again, so this part, U minus transpose F transpose. And now naturally we came to the situation when we have here this U we have here that F brought together, F transpose F. But this was nothing but F transpose F. That was in fact our tensor C, right? So that was right Cauchy-Green tensor that is also by definition equal to U squared. So then we can write that this is U squared. And so one will things that we did here, we recall that U also C is a symmetric tensor, so we can transpose it and it will be the same. So from that U squared, that will be U multiplied by U, but suddenly we wrote U transpose U here, right? And in general, you cannot do that, but here you actually can, because what we did here, so this was U squared, which is nothing but U multiplied by U, but because U is symmetric, so U transpose is equal to U. Obviously, for the same property as C transpose, we can readily put here transpose, and that will still be correct. Now, once we did that, so that becomes very helpful for us, because because then we can identify these two things, U multiplying U minus transpose, so by definition that will be identity tensor here, right? So that this inverse of the same second order tensor, and the same thing is here, because this is again an inverse of the same tensor, which is U transpose here. So that will be identity tensor, and then as a result, so to identity tensor multiplied, we obtain the identity tensor again. So what we have seen is that so this is an essential property, is that when we multiply of the orthogonal tensor, is that the transpose of that multiplied on multiplying itself produces identity tensor. Okay, so and again that's on the level of tensor properties. But what is important for us that these tensors, when they act on vectors, so they do not change their length. And again, so that is an important part of in the deformation gradient that tensor R does. It does not change the length of the vector. So that job is due to the stretch tensor. Okay, so we can actually see that. So for example, let's assume that we don't have no any stretch, and so let's say our deformation gradient f only consists of R. Okay, so and so then we can write. So we had so this is the length of our small infinitesimal line element at a point. We called it dy, and so so this is the length of that. So it's the root square of the dot product dy. And dy we can write. Typically, we would write it differently. So we'll write it. We would write. We would write that dx or dy is equal to f dx. But now we're saying that, and we said that, okay, let's say that f is nothing but is nothing but ru, right? Here, and so now we're saying, okay, so let's say there is no stretching, and just okay, so let's say there is no stretching, and let's say that u is identity, right? So there is no stretching going on, and then, okay, let's put if here, okay, and then that would mean that f equal to r, right? And so only rotation is present at that point, and therefore then I write that dy and dy is equal not f, or I could write here ru, right? So but it will be equal to just r because we said u is identity. Okay, so and so we use that here. So basically wrote that dy is equal r dx, and so now we can use already a similar transformations that we had. So we can rewrite this multiplication r dx such a way that we change the order, and so and to do so we need to, and we just did that with another multiplication. So we need to add transpose to r, so we maintain the same order of of multiplication, and so our indexes and components are not mixed up. So that will be dx dot product r transpose. So we already have seen that before, right? So exactly this part, right? So that's and in that way we maintain the correct order of multiplication, right? So but we must add the transpose here. And then here, if we look again at what we got here, is just, okay, this is r transpose r. So when they multiply here, it's our exercise that we did for r transpose r, the result will be identity. So instead of r transpose r, here we can write identity, and then identity multiply dx. Of course, the identity tensor doesn't transform any vector to anything, so it just remains the same, dx. And so we have dx, and that means that the original length, so the length of that new vector in the deformed configuration of that line element will be exactly the original length of that same line element before the deformation occurred. So again, well, that makes sense. Of course, the rotation tensor doesn't result in the change of the vector. It can, so the vector can change, but its length is preserved. So this is important. So another important property, so this rotation tensor, what is called proper orthogonal, some orthogonal tensors can be improper orthogonal. and that's typically you can tell that based on the sign of the determinant of R. And so we can look into the determinant R. So if it's positive, it's called proper orthogonal. If it's negative, it's improper orthogonal. Our guide, the rotational one, is what is called proper orthogonal. Now, so we can do that. We can calculate the determinant of R again based on the same formula that we had. So that F equal to RU. So determinant of F equal to determinant of R multiplied by determinant of U. So determinant of R will be determinant of F divided by determinant of U. So we can write that. So just using these properties, and so and then we can go ahead and say, okay, so there is a we can write the determinant of F. It's still so the transposition doesn't change so that you will get the same determinant even if we calculate determinant of F transpose. And so then we can write this that F, we can say, okay, we can multiply it with that F, and then we can say that this is also that F transpose, and we will calculate the root square of that. It still will be the same that F, right? So that's what we did here. So basically that F transpose is the same as that F, and so multiplication of this can be written as determinant of F transpose multiplied by that F, and of course the root square of that will be still giving you determinant of F here. And so we did this intentionally because we wanted to get the structure that F transpose F, which is nothing but our right Cauchy-Green tensor, which is C. So we have root square determinant C, but we also said that, okay, so we defined the stretch tensor U through C, so C was can be translated as U square, right? So that's what we had on the previous slide, and so we have determinant of U square divided by that U, and very similar to what we just did from transforming that F into this root square that F. We can also do for that U square, so because that's of course that U multiplying that U root square. Okay, we just can remove the square sign, so that will be that U divided by that U, and so we arrive at determinant of the rotation tensor is 1, meaning that we have the what is called the proper orthogonal tensor R. So he's the proper orthogonal. Okay, so then the last thing that we'll do actually will visualize this transformation for decomposition, how this mapping is working. All right, so looking into this visualization, all right, let's look into our original configuration here. And so this is our line element at that point. This is dx, and so we have so we decomposed our deformation gradient into these two creatures, R and U. So when we come with the deformation gradient F and multiply this vector dx, so eventually we will obtain that dy, right? But the structure of F that we said it is RU is such that first we multiply this dx with U, and this is stretch tensor, which when we apply it on dx, so we are going to stretch this line element. So this stretching is applied here. All right. And then after that, so the second multiplication of this new vector u dx is with R, and then we obtain the new vector dy, right? So dy is nothing but a sequence of multiplication of transformation of dx, first by stretching, so we can multiply u by dx. That's exactly the operation from here to here. So I obtain u vector u dx, right? So u acting on dx, and so this is a new vector. and then finally this new vector is rotated by the rotation vector r, and so then we obtain that dy. Well, again, alternatively, what you could do is just in one step coming from dx to dy by multiplying it df. Well, interestingly, we can go in the opposite order. We actually can first rotate it, the vector, right? So we can write it differently. So we can take that the same dx, apply the rotation, and then the length of that line element doesn't change, it just rotated. So the new vector is r dx, and then we are applying this stretching operation, and so we are supposed to arrive exactly to the same vector dy. So with just different sequences. And the thing is, and then what we did, we took that dx but multiplied in different sequence. So we had that. So we first rotated this with r, and then multiply and then stretch it with v, right? So then v, in general, v is a different tensor, not as u. And of course, it's the same as we go directly from this configuration to from the undeformed configuration to deformed configuration, just with by multiplying this vector dx by f, as I have indicated here. So there are basically two ways how we can see this decomposition. And therefore, okay, so we defined this right stretch tensor u, but there are also possible to define all these operations through the so-called left stretch tensor v, right? So it's then so we can again define f through right stretch tensor or through the left stretch tensor. So that meaning the important thing here to realize is just that changes the order, a sequence of things that we do when we transform this original vector dx into the deformed line element, that vector dy. Right, so that is. So now we can formally also define the left stretch tensor and all the mechanisms that we have here, similar to what we did with the right right stretch tensor. Now we can basically just use the new definition of our transformations, deformation gradient decomposed in this order with v and r. So we can just directly write what v is, and so we can just multiply f with inverse r, or we can already start using the properties of r. Right, so that's r. The inverse of r is nothing but the transpose of r, so the same effect, because we know that this is the orthogonal. Oh, this is the rotation tensor is has certain properties, right? So that we just showed that it's the orthogonal tensor, the transpose of that tensor has the same effect as the inverse of that, so that basically the same tensor. This is one of the properties, and so we can then just directly write this from 232. We can multiply this r inverse r, so then we have v from here from 232. But we also can note that inverse of r can be written as r transpose. And then further we can just go ahead and write here that and then from here we just we can use, instead of f, we can also use our usual the first decomposition with the right stretch tensor, and then we can write that it's nothing but ru, as you can see here. And so, and by looking into this structure, you can see that v is nothing but the rotation because that's how you rotate the second order tensor by multiplying with the rotation tensor R and R transpose from left and right. So V is the result of the rotation of the right stretch tensor, and it is also symmetric, right? So that and so therefore what will happen is that the eigenvalues of C, so the principal stretches that are defined for V and U will be the same. However, the principal directions can be in general different. And so again, for U, so we have written it before through this through the Cauchy-Green tensor. So we had this simple structure of these lambda stretches in the directions in the principal directions in the undeformed configuration. However, for V, the structure will be similar, but the difference is such that we actually have here a new vector n, and so by looking into this structure of relation between V and U, we also can write it explicitly what this vectors n are. So because they are nothing but so we basically, you come to that tensor U and multiply it with R from right and R transpose from left, and then you obtain V, right? So that means that these tensor products of, for example, n1 and 1 and 2 and 2 and n3 and 3 are obtained by multiplication of this m1 and 1 and m2 and 2 and m3 and 3 by R from the right and R transpose from the left, meaning that so they are related by this formula again, and so that we also were able to again change the order by changing also the transposition of R disappears as we change the order of that, as we push the R transpose from multiplying from the right, so that change the order here of the multiplication. And so it's similar to what we did before, just with multiplication, and change the order of when second order tensor multiply the vector, so the transposition is gone now. And so we have a new vector, right? So this V is based on a new vector in the deformed configuration. Actually, we can go back into our our illustration here, right? So and it does make sense as we apply this stretch tensor in this principal system in the undeformed configuration. So it's so they still preserved, right? So it's not rotated yet, and only then it is rotated into the new deformed principal system, right? When we go with left with this sequence, first rotate and then apply left stretch tensor, so what we do, we map that our initial undeformed line element as vector dx into the new one, into the rotated one in n1 and 2, okay, in 2 dimensions, and so and then the principal stretches are already calculated in this deformed configuration, right? So the V is the stretch tensor for the principal directions in the deformed configuration. So this is the change in N and M. And so N and M are mapped in the continuation through the rotation tensor, so because basically they were rotated. And so now, based on that new order of deformation, right? So we again, so rotation first, stretching after. So we can define the new deformation tensor, which is also called left Cauchy-Green tensor. So we had right Cauchy-Green tensor. Now let's look into the left Cauchy-Green tensor. And so for that, and similar to what we did for the right Cauchy-Green tensor, which was related which was related to the square of the right stretch tensor, which was u square. Now let's look into the we're doing this in a little bit reverse manner. So we have the stretch tensor, the left stretch tensor. So let's increase the power. So it's so we expect the square here, and then we use the formula. So it's basically multiplying. This is u and this is u again. Let me change the pen. So this is this is v, right? So multiplying v again, so this is also v. So that's by our definition for the left stretch tensor, we were able to obtain that. Now by looking into this structure, we also we also can see immediately identify the multiplication that will not produce anything. So this identity tensor here, right? So this R transpose multiplying R, because it's orthogonal tensor R, or the rotation tensor, that will be identity. So we end up with having RU multiplication with UR. So and RU is very convenient for us because this is a deformation gradient F, right? So we can keep this guy. And now what we want to do, we want to transform this guy into something that will also have an order of RU. And so how do we do that? So we need to transform this UR into the something that will be looking like RU. So that one way to do that is to actually to transpose that. So we apply transposition on this UR, so that will be but actually will be RU transpose, right? So if we transpose this whole thing, so that will be RU transpose. But U transpose is also equal to U, because it's a symmetric tensor, and so we can say that this UR transpose, and then and then that will be RU is already convenient for us F, right? But we cannot simply just come here and say, okay, this is F. So we need to transpose that. It's either this is equal to F, or this whole thing UR transpose is equal to F transpose. Or basically we can just say, okay, let's write this UR transpose as this RU but transpose, and that will be correct. Right, so we can write that, okay, so we don't touch this is still the same RU, but we are saying that this UR transpose is nothing but RU transpose. So we can actually prove that very easily, because RU transpose, we just have seen that, is equal to U transpose multiplied by R transpose, right? And U transpose is equal to U, so basically exactly we're getting the same result as was originally here. So it was U R transpose, because U is symmetric. And so then we can write that V square is equal to F multiplied by F transpose, because these both are F, right? And that leads us to the definition of the left Cauchy-Green tensor. Typically is denoted by B, and so that is that's how we define the left Cauchy-Green tensor as typically this is the definition F transpose. And the difference with right Cauchy-Green tensor is that where this transpose stands, so that actually changes quite a lot. And so then the again, based on the very similar logic, we can write it into the spectral decomposition through the principal stretches, right? So that will look like that. The difference with the right Cauchy-Green tensor will lie in the difference in this in the principal directions. And again, so here B will be written in terms of the of these vectors that are already after the rotation. So they're deformed in the principal direction in the deformed state. Whereas for C, for the right Cauchy-Green tensor, we would have here the dyadic tensor products of M and M, and those were again in the principal direction in the undeformed configuration. So the mapping between them is defined through, again, the rotation. And we've seen that basically the M is still where we had it identified this direction in the undeformed configuration. Then after that we rotate it, and that's where we obtained the new principal direction from which we, for example, if we follow the left stretch tensor, then we started stretching them from that. Now, one last thing, so we can write the try to write the spectral decomposition of the deformation gradient itself. Also, however, that will lead us to somewhat strange situation. So, okay, so we can that may not be very convenient for us to follow, right? So we will have this. We can write the definition of f, right, which is RU, and then we can look back into the definition of U, and so that will be exactly this. So this U is U will be these components here, including M but not including R, right? And so now we come with this R here, so right, we can pull outside that lambda because it's a scalar, and then we multiply with R from the right and from the left, obviously. And so when we multiply, we come here with this R and multiply this. And again, so this is the component U1 that correspond to M1 for U, and this another component corresponding to U, right? And this is another component corresponding to U. And now we came with that R, multiplied it from the right, or from the left again, and so that R obviously is acting on that first M, right? So that here, right? And so and it transforms it basically rotates it into a new vector, and that vector will be n1, n2, and n3, in depending on which of these m's R is acting. So we're just using the formula 238, right? So, and to calculate what's going on here when we multiply this R with M, and therefore, so the result at F will look like that, right? So we'll have a mixture of this N1 and M1 tensors here. This second order tensor that is based on two different types of basis vectors. So one of them, N, is in the deformed configuration, while M is in the undeformed configuration, and that again connects us to the first time when we mentioned that the deformation gradient F is the a 2-point second order tensor that has kind of one leg, one basis in the undeformed configuration and the other basis in the deformed configuration. So here, when we try to write the spectral decomposition for the deformation gradient, then we ended up with this mixture of the combination of the basis vectors. Whereas again, going back to our for example, left Cauchy-Green tensor, so the spectral decomposition clearly is written based on the principal directions or eigenvectors in the deformed configuration. If we go back to the right Cauchy-Green tensor, then we obtain the multiplication here, dyadic products of m of vectors m, which are the principal directions in the undeformed configuration, so they don't have this mixed up situation. So therefore that's important for us to actually to use either B or C, the right Cauchy or left Cauchy-Green tensor, as we continue defining the ways how the material behaves. All right, so we'll stop here, and then we'll we'll be talking about measures of strain, and I will use this these different measures of the right or left Cauchy-Green deformation tensors, so to define or redefine how and what we understand by strain in our next lecture. See you then.